Hello, Stanley Lake, Mrs. DeMink here. Chapter 14, Chemical Kinetics. So the last of the big three topics in chemistry. The first one being thermodynamics, which was just kind of, how much heat does a reaction need to take place? Does it release heat? Does it absorb heat? The second being equilibrium. To what extent does the reaction go? Does it go to completion? Is it more to the left, more to the right? And then chemical kinetics. How fast does a reaction take place? Lots of different reasons why this is super important, especially in industry. Many times you want a reaction to speed up. If you take a medicine and you want it to be fast acting, that's all about what is the rate of reaction within your body. And the flip side, why would you want to slow down a reaction? If you want something more time released, or a reaction to slow down the destruction of the ozone layer. So lots of different applications for chemical kinetics. So we're going to start out by looking at it sort of mathematically. How do we calculate, since we're talking about rate, looking at change in things over time. So we've got a little bit of math to do here, some calculations of reaction rates and rate laws, and a method of initial rates is a little way that will show you how to calculate those things. And then kind of moving into sort of the molecular version of it. So how do these reactions actually take place, and what can we use to kind of speed them up? So this idea of reaction mechanisms and catalysts. So let's get started by talking about introduction to the reaction rate. What are the units that we're going to be using? So since we're using a change in molarity, a change in concentration, because we're doing change of product, or change of reactants, the units of reaction rates are always molarity per second. And so there's a variety of different ways that you're going to see this. You could use the big M, you could write it moles per liter, which of course we know is molarity per second. Books might write it also, using this notation instead of putting it as a fraction, so whatever works for you. How do we determine reaction rates? Well, we've got to use the chemical to measure the rate. Whatever chemical we use is the one that is easiest to measure. Whichever one is the easiest one to observe in a chemical reaction. So for instance, if I take a little zinc and I throw it into some hydrochloric acid, and I remember we did this as a demo a couple times, I will produce zinc chloride and hydrogen gas. So if I wanted to see how fast this reaction would go, I'm going to look for some visible signs. Since I'm using hydrochloric acid, I could measure a change in pH. It starts out pretty acidic, how it goes down to when it makes zinc chloride, I could measure that. I could look for color change. Zinc chloride is sort of a black substance, so the appearance of that black substance. Or since hydrogen gas is a gas, I could measure how much hydrogen gas I create. So all of our experimental data is pretty much based on whichever one is the easiest to see out of the reaction, the easiest one to measure. Okay, so let's take a look at this example in terms of what does a reaction rate look like. So we're going to kind of use this example. Reaction rates are going to be totally based off of experiments, so we're going to need some data. And then we can plot these lovely little graphs to kind of get a sense of how are things changing. So if you notice, we've got the initial concentration of NO2, that's our little green line here, 0.01 molarity. So we've got concentration on our Y, and we've got time down here on the X. And what we kind of notice is how this graph is sort of, our line is kind of going down like this. So you see how the concentration is decreasing over time. Now as the NO2 decreases, of course you see how the NO and the O2 increase. And if you kind of take a look at our stoichiometry of the reaction, you see that the NO is increasing twice as fast as the oxygen, or the oxygen is increasing at half the rate, which would be more accurate because your NO2 and the NO, since that's kind of a 1-to-1 ratio, you kind of see how the O2 would be increasing at a rate of half. Now if I wanted to know my overall rate, now this would be really easy if this was a straight line. I could just take 2 points, figure out the slope, done. But since this is a curve, when I have a point on a curve, really all that's going to give me is an instantaneous rate at any given time, and that's not terribly useful. We need to know the overall rate. So kinetics is totally based on calculus. How do you figure out the slope of a curved line? But the good news is you don't actually have to do the calculus for this. So it's based on it, but all you really need to kind of know is calculus exists. It's a really great idea, but we don't actually have to use it for this particular chapter, which is good for me because I don't remember my calculus. Don't tell Mrs. Humphreys. Okay, let's just take a look at one kind of typical example that you might see as sort of a multiple choice question, really dealing with kinetics. If the reaction rate for my above reaction, meaning the NO2 and the NO and the O2, is 3.2 times 10 to the negative third molarity per second for O2, what is the rate of disappearance for NO2? So let's see, my rate, so rate is change over time, change in molarity over time. And if you kind of go back to the idea of the stoichiometry of the reaction, this is a 1-to-1 ratio, and then that's like half of it. So this is going to be kind of a pretty easy question. If I'm looking at the disappearance of NO2, and I know my rate for O2, all I really got to do is this. Now that's not meters per second, don't use your physics, this is molarity per second. And so if you just kind of double that, that gives you your rate for the disappearance of NO2. A lot of kinetics you can kind of solve just by using some dimensional analysis. So, all right, rate laws. How do we come up with these magical rate laws? So let's just kind of use a generic equation. 2a plus b gives you c. To write a rate law, what this would look like, so the rate law, I'm just kind of say rate, is equal to k, which is a rate constant, and we're going to have to figure that out through experimentation, times the concentration of A raised to the x power times the concentration of B raised to the y power. The values for x and y are also can only be found by experiment. That is not the coefficients. So the rate laws are actually kind of independent of the stoichiometry. So A to the x and B to the y, whatever kinds of reactants you have, and what you're trying to figure out is just basically kind of the overall, what's the change of concentration over time. Determining your overall rate order, really all you have to do is add up the exponents. So if you have a rate law, rate equals k to the a, this is called a first order reaction. If I have k to the a, this should be a little exponent up here, squared. This is a second order reaction. If I have k times a times b, this is also a second order reaction. If I have k times a times the b squared, this would be a third order reaction. There is actually a zero order reaction. Should put this kind of off to the side. And we'll see that actually in a lab. I think we come up with a zero order reaction. But if you think about it, if I have the exponent of 0, really your rate is just going to be equal to your constant, because a to the 0 equals 1. So you will see all those types of things. Third order reactions are pretty rare. Most of what we deal with in AP is going to be 0, first or second. Units of K, pretty standard question on the AP exam, is involving calculating the units of K. Good news is, totally dimensional analysis, so you guys should be fine. The units of K depend on the order of the rate law. So let's kind of go through the different types here and see what we come up with. So if I have a first order reaction, so my rate is going to be K times a to the first. Now how would we come up with the units of our rate constant? So keep in mind that rate is molarity. Let's not do that. Let's do moles per liter, so you see it this way. So rate is molarity per second, right? So that's my unit of my rate law. I don't know what K is, but I know what A is. Those little brackets mean concentration, so that's moles per liter. And if you kind of do a little dimensional analysis, this comes up with your K as being 1 over seconds. You could also write it as seconds to the negative 1 if you desire. If you have a second order reaction, let's say my rate is equal to K to the A squared. We'll just keep that simple. Again, your units of your rate law are always going to be molarity per second. Let's call this molarity. Pretend that's moles per liter. Equals K Now since this is concentration squared, I'm going to think of this as being moles squared per liters squared. Alright, I should really be consistent in my use of big M's and liters and so forth. Sorry guys. Let's call it molarity squared. Keep it simple here. So now I got to get K by itself, and the dimensional analysis will kind of show you that you end up with molarity per second divided by, I need equals, molarity squared. So if we simplify this down to one of my molarities is indeed going to cancel, my units of K would end up being molarity per second. A third order reaction. So let's say my rate law is K times A times B. Oh, let's put a little squared in here by the A. What would my units of K be? So I'm going to KB. What would the units of K become? We're going to do molarity over seconds. It's always your rate. Solving for K. This is molarity squared times molarity. So that's really molarity cubed. Rearrange, solve for K. I do end up with 1 over molarity squared seconds. Okay? Easy way to look at it. Alright, the method of initial rates. How do we then go ahead and calculate the rate? How do we get that number of what the rate would actually look like? So the method that we use, you're going to pick 2 experiments, because remember this can only be determined experimentally, such that all but one of the variables cancel out when divided. So I'll kind of give you show you that as we go through an example. You set it up to look kind of like this. Rate 1 divided by rate 2. It doesn't really matter which 2 experiments you pick. Usually when I do these, I tend to put the bigger one over the smaller one, because you come up with whole numbers, and our goal is to get the exponents, to figure out what x and y are, and so you want them to be whole numbers. So usually by doing the bigger one by the smaller one, you get your whole numbers, but it doesn't really matter. Cancel all but one of the exponents and then repeat to find x and y. Use one of them to then plug and chug one of the experiments, when we say use one, to determine your value of K, so figure out what the rate constant is equal to, and then use your dimensional analysis to figure out the units of K, which we just kind of went through. So let's do an example. Using experimental data. So determine the rate law given the following information. So we've got ammonium ions reacting with nitrite ions to give me nitrogen gas and water. Alright, so the first thing that I'm going to do is I'm just going to write out what my rate law would look like. So I'm going to have a little NH4 plus to the X, and then NO2 minus to the Y. Wow, I gave myself a lot of room for that. So that's my basic form of the rate law. Now what I have to do is I have to figure out what X and Y are. Is this a first order reaction, second order reaction? What do I do? So using the method of initial rates, I'm going to look at my pieces of data here. Now if you notice, between experiment 1 and 2, the concentration of NH4 doesn't change. And between experiment 2 and 3, my concentration of NO2 does not change. So first I'm going to start by using experiment 1 and 2. So I'm going to put experiment 2 over experiment 1. Why? Because when I look at the rates, 2 is bigger than 1. Equals, so I'm going to write the rate laws, plug in numbers from the data, 0, 1, 0 to the y, divided by my nice straight line, 0.100 to the x, 0.0050 to the y, and this is equal to 2.70 times 10 to the negative 7th divided by 1.35 times 10 to the negative 7th. Okay, so I've set up my rate laws, dividing the 2 experiments. Now I want to look and see what kinds of things can cancel. So my K's automatically cancel, that's cool. This 0.1 to the x, 0.1 to the x, that cancels. So that's handy. So now that just simplified my math a whole lot. So from here, hopefully you can kind of do some of this in your head. If you notice, 0.01 divided by 0.005 is 2. So 2 to the y power equals, well, 2.7 divided by 1.35 is also 2. So what would y be? 1. So we know that the exponent for y is 1. Now I got to figure out what x is. So now I'm going to pick 2 other experiments to solve for x. So I'm going to look at experiment 2 and experiment 3. So I'm going to set up my rate laws again with experiment 3 divided by experiment 2. Why? Because number 3 is bigger. You can do it in the reverse. It doesn't matter. The math just comes out a little easier for you because it comes out with whole numbers. So what do I have here? Experiment 3. So we've got 0.200 to the x times 0.010 to the y divided by k times 0.100 to the x, 0.010 to the y, and I have my rates. Wrong. 5.4, not 2. 5.40 times 10 to the negative 7th divided by 2.70 times 10 to the negative 7th. Okay, so now you want to look for stuff that cancels out. Your k's should cancel out, so you're good there. My y's are canceling out, so we're good there. And now your math is a whole lot simpler. So if we look at this, let's see. 0.2 divided by 0.1 gives me 2 to the x. So I got that. 5.4 divided by 2.7 is also 2. So guess what x is equal to? 1. So now I am good and ready to write my rate law. And so the final answer would be my rate is equal to k times NH4 to the first power NO2 to the first power. That's a 1. That's not too hard. Let's try another one. Consider this reaction of some stuff with some iodine, and there's a really nice looking reaction there. I don't even really know the perioxydisulfate ion. There you go. At a particular temperature, the rate of disappearance, and this is a multi-part problem, so let's jump right in. So the first thing that I kind of want to do is I'm just going to sort of write my overall rate law, so just so I get a picture of what I'm trying to accomplish here. What are my reactants that are involved in the rate law? So this is going to be to the x, and then I got iodine to the y. And say this data comes from experiments, and we're going to be doing labs where you guys create your experiments and figure out what the rate of a particular reaction is. So let's go ahead and get started with the letter A here. Determine the rate law. So using our method of initial rates, I'm going to look for the biggest one where something can cancel out. And as you kind of look at this data, none of this is the same. These two are the same, so that might be useful. So what I'm going to do, I'm going to take experiment 2 and experiment 1 and use that to figure out one of my exponents. So let's do experiment 2 divided by experiment 1. Let's see, experiment 2, its rate is 3.9 times 10 to the negative 6th. So that equals K times concentration. That is to the x power times my concentration of that to the y power, all divided by the information for experiment 1, 2.6 times 10 to the negative 6th, K 0.018 to the x divided by 0.036. So this is nice because I got stuff canceling out. My y's are canceling out. My x's are canceling out. So now I can solve for x. So this ends up, when I divide 3.9 by 2.6, that comes up to be about 1.44-ish. And when I divide 0.027 by 0.018, that comes up to be 0.15. Those are close enough to being equal. I mean, keep in mind, guys, these are experimental values, so of course there's going to be a little bit of error. So you just kind of want to get it close enough that you can call it. So we know that our x is going to be equal to 1. Do I have another blank screen? Yes, that would be super helpful. So now that I know my x value, I'm going to figure out what my y is. And this time I'm going to take experiment 3 and experiment 4. So you don't want to take the same two that you did, so you look for something else. But as you kind of look through all this data, you know, these two are nice. They canceled out and so forth. Nothing here is held constant, so nothing's really going to cancel out, but that's okay. Just pick 2 experiments. It'll work out. So I'm going to do a 3 over the 4. Okay, so my rate's 7.8 times 10 to the negative 6th divided by 1.4 times 10 to the negative 5th equals k times 0.036, 0.054, that's to the y, this is to my x, which I know the value for x, but oh, I do want to put that in. Since I know my x, I'm going to go ahead and say that this is to the first. Since these aren't going to cancel out for me, that's kind of important. And that's to the first, 0.072, 2 to y. Okay, looking for things canceling out. Well, in this particular case, only my k's cancel out. The rest you're just going to have to kind of plug and chug here. So divide these two numbers, I get that. My k's cancel out. This ends up to be 0.72 when I divide 0.036 divided by 0.050. My other two numbers, this ends up being 0.75 to the y power. So now I got to solve for y. 0.77, if I start simplifying here, 0.75 to the y. Close enough. I will call that 1. Alright, so now I know my official rate law. The answer for letter A equals k times S2O8 to the first power. And the iodide ion is also to the first power. So there's your answer for letter A. Letter B. Now we've got to determine the value of k, including units. So here you're just going to pick any one of these experiments. It doesn't really matter. I am just going to pick the first one. And here all you got to do once you got your rate law is plug and chug. So let's plug in the data for the first law, or the first experiment. I'm going to figure out what k is. Use the concentrations. I got my exponents. Okay. So you go ahead and you solve for k and you end up with 0.00401. And then units, use your dimensional analysis, since I got molarity times molarity over there on the one side. My units for k end up being molarity per second. If you're using this m, be careful that you're not saying like meters and seconds and that sort of stuff. Not physics, chemistry. Alright, let us see. How is the rate of disappearance of S2O8 related to the rate of disappearance of I3? Well, if you look at the stoichiometry of our particular reaction here, the answer should kind of pop out at you. What's the relationship between the S2O8 and the I? That's right. There are 3 I's for every one S2O8. It's easier than saying the peroxy, blah, blah, blah. So really, your answer for this is just that your rate of disappearance for I, disappearance, I can spell, of I is 3 times as fast, because it's a 3-to-1 relationship, stoichiometrically wise. Letter D, almost done. What is the rate of disappearance of iodine when the other stuff has some concentrations? Alrighty, well, let's plug in to an experiment. What do we know? So here we're going to be solving for the rate using our rate law. So we don't know the rate. We do know a value for k. We just figured that out, 0.00401. And then this problem gave us some concentrations, so I'm going to go ahead and use those with the appropriate exponents. They're all to the first, so that should be good. So our rate is 2.4 times 10 to the negative 6th. And don't forget the units. Don't forget the units. Molarity per second. And that, guys, is how you figure out a rate law. We will get into the rest of this chapter in other podcasts. Have a good one.